Welcome to Year 2 Pure Mathematics, Sequences and Series, Lesson 4. And today we're going to look at the formula for the sum of n terms of a geometric series. Okay, and we're also going to look at an idea called the sum to infinity, which applies to convergent geometric series. For the warm-up, you're going to need to use the definition here of a binomial expansion that we looked at in a previous chapter. Okay, so please pause the video and try the 4 warm-up questions. Okay, and let's have a look at the solutions. So question 1, we have a rational expression here, a over 1 subtract r, and you're asked to find an expansion up to the r cubed term. Well, what we can do is we can just rewrite this as a exponent. So if I just say this is equal to a multiplied by 1 subtract r, and then obviously r is raised to the power -1, we have an equivalent statement, don't we? And we can now use the binomial expansion on this part of the expression we've just written. So we just need to state what a and sorry, beg your pardon, we just need to state what b is for this, and of course n. So my b is -r, and my n is -1. And now we can sub those into the binomial expansion. So what I'm going to do is we're going to need a little bit of room for this, as you may have noticed already. So we're going to change that. So we're going to say, okay, this is equal to, I'll just box that off, a, and then I'm going to open some big brackets. And then we can start to write out the binomial expansion. So you have this definition above you, in front of you, above the first question. So this is going to be 1 plus -1, which is the n multiplied by b, -r. And if you like, you can say that's divided by 1 factorial. Okay, we know that's 1, so it's not necessary really. And then for the third term, it's going to be -1 multiplied by -1 subtract 1. And we divide that by 2 factorial. And don't forget that this is going to be multiplied by -r squared. Next up, we've got the third term. So this, the fourth term, sorry. So this is going to be -1 multiplied by -1 subtract 1 multiplied by -1 subtract 2. This is going to be divided by 3 factorial. I'm just encroaching on question 2, but never mind. And then we take our -r, and then we have to cube it. And there may be more terms to come. So just to acknowledge that, I'm just going to say plus ... And let's close our big square brackets. So we just have to tidy this up now. So this is going to equal a, open your bracket, let's do some tidying up. Well, 2 negatives make a positive, so that's going to be plus r. And then we have add -1 multiplied by -2 over 2 factorial, which is just 2. And then if we square -r, of course, that's just going to give us r squared. And for the last term, we're going to have -1 multiplied by -2 multiplied by -3 over 6. And then -r cubed, just be careful with this, should be -r cubed. Okay, hope that makes sense. Then we're going to add some more terms if necessary, but it's not necessary. Close your big square brackets. Okay, let's do a little bit more tidying up. So this is going to be a multiplied by, okay, so 1 plus r. Lots of cancellation here. This is just going to give us plus r squared. And we're going to have -6 on the top for the r cubed term. That's going to cancel with the 6. So we're going to have, and 2 negatives make a positive. So that's going to be plus r cubed. So that's rather nice, isn't it? And then we've got plus ... All right. So this is a very nice expression. Let's multiply all this by a. And our final answer is going to be A plus AR plus AR squared plus AR cubed plus some more terms that we're not going to write down. Now, immediately, I'm hoping alarm bells should be ringing now. Where have we seen this before? Well, these are all terms of a geometric sequence, aren't they? Okay, and notice that we're adding them together. So perhaps this is a geometric series. But unusually, as we've already seen, we have another way of representing this series, and that's here, A over 1 subtract R. So is this really equal to A over 1 subtract R? Well, if we go back to our work on the binomial expansion, remember that there is a condition, isn't there? Okay, there is a condition whereby the B part of our expansion, so in this case that would be negative R. I'll just highlight that. The B part has a restriction, doesn't it? Okay, what is the restriction? You should know this. Well, it has to be between -1 and 1, doesn't it? So although we have a question mark over this, we could say, well, this would be valid if the negative R was sandwiched between -1 and 1. In other words, if R was between -1 and 1. So just think about that. When we get to this later, you'll see how it all fits together. But I think that's quite an interesting result. Let's move on to question 2 now. So this time we've got a geometric sequence and we have to find the nth term rule. Well, okay, well, this is sort of standard stuff that we did in the last lesson, isn't it? So we state the first term, which is here, which is of course 1. So A is equal to 1. And then the common ratio R, well, just take any 2 consecutive terms and divide the latter by the former. So if I took 1 over 8 and divided by a quarter, that's going to give me a half. Or you could take a quarter and a half, but it doesn't really matter, or 1/16 and 1/8. Whatever you do, you're always going to get a half. Okay, so that's the common ratio, the multiplicative factor that creates the sequence. So UN, using the general form, is equal to A R to the power n subtract 1, which is equal to 1 multiplied by 1/2 to the power n subtract 1. In other words, my sequence is going to be a half to the power n subtract 1. Okay, and we've done. So for questions 3 and 4, I've just filled in the table for you and I've plotted the graph as well. Just a few things to note here. The function, which is very similar, obviously, is the continuous extension of the sequence you've just found in question 2. But this function is only defined for x is greater than or equal to 1. So make sure you start your graph at the same point. And I've asked you to round to 2 decimal places when appropriate. It's just so it's easier to plot. So that would obviously affect these 3 values here. Okay, so we plotted all the points along here. So that's 3 done. And then for question 4, you're asked to state the limit as x approaches infinity. Well, if you do that, let's just have a look at what happens as x gets larger. Well, obviously the graph is approaching the x-axis. And you can verify this as well. If you just take any large x value and substitute it into your function, you'll notice you'll get a very, very small but positive number. So we can state with confidence that if you take the limit as x approaches infinity of this particular function, you're going to get 0. All right, and that concludes the warm-up. So here it is. This is the sum of a geometric series, and there are 2 actual general forms to this that we can use. There's the 1 subtract R version, and then there's also the R subtract 1 version. You can use both of them interchangeably, it doesn't matter. And there are situations where you may prefer one over the other, but that's down to your own discretion and the situation in the question. All right, let's look at the proof. Now, this proof, you notice it's set out in a similar way to the sum of an arithmetic series. Don't be fooled by that, but it is quite similar, but there are key crucial steps. Now, I will point them out, and if you remember them, that will be the key to reproducing this proof in its entirety and accurately. So let's write it out. So we're going to call the sum of n terms Sn, and it just represents this formula, okay, which we'll see shortly. Okay, both of these are Sn. All right, now when we add up the sum of n terms, which is what this means, I'll just remind you. It's this sum of n terms. What we need to be aware of is I'm adding all the terms up to the nth term. I'm going to stress that. So it's the first term up to the nth term. So let's write those down first. So if we put in the first term as a, then clearly the nth term is going to be ar to the power n subtract 1. Okay? Remember, that's the general term of a geometric sequence. And if we start to put in the rest of them, we're going to have ar squared, bringing in the common ratio. And it might be helpful to work from the right back towards the center. So let's think, what would the term before the nth term be? Well, that's the n subtract 1th term. And remember, that's going to have it's going to be one less in terms of natural numbers than the nth term, isn't it? Okay, so if we take 1 away from n, we're going to clearly get n subtract 2. I hope that makes sense. Okay, and then if we go 1 prior to that one, it's going to be ar to the power n subtract 3, because we're always adding 1 to the n as we move along the series. And remember, this is a series, so we need to put in the additions. So it's going to be a plus ar squared plus some more terms. And then we're going to finish off with the nth term. Now, just to remind you, this is the nth term because we're summing the first n terms. Okay, and you might think, okay, what we're going to do, we're probably just going to write it backwards. Well, you'd be wrong. What we're going to do is, this is the first trick I want you to remember. So if you write out the series like that up to the nth term, and then the next step is you're going to write it out again. Okay, but this time we're going to multiply the whole thing by r. So this is the trick. That's a crucial step. I think it's so important. I'm gonna have to highlight that. So let's do that. So this is the crucial step here. Please remember to do this. So let's just take the sum of n terms and multiply everything by r. Now let's see what happens here. Why do we do this? Well, let's just see. So this is going to be ar squared, adding 1 to the power of r, ar cubed. And if we add 1, obviously that's just going to be the same as ar to the n subtract 2. Then we have ar to the n subtract 1. That was the nth term, wasn't it? And then we have to multiply the nth term by r. So I'm going to add another n, or another 1 to the n subtract 1. So this is going to be ar to the power n. Okay, I hope that makes sense. So you're just adding 1 to each of these powers. Great, and let's put in the addition symbols. So adding all this together. Now the question is, do you notice anything interesting? Well, there is some similarity, isn't there? If we look at the diagonals, we have similarity there. We have similarity there. If it was written in, there would be similarity there. Similarly here, here, and here. Now, could we create some kind of cancellation? Well, yes, we can. And that's what this space is for. Just think to yourself how you would do this. You might want to try this step yourself before I do it and just pause the video. Okay, well, if I take my summations and if I subtract one from the other, I'm going to get this. So if I do Sn subtract Rsn, so I'm going to subtract in this direction. Okay, what happens? And this is the exciting bit. So what you're going to get is you're going to get A. So it's the first row subtract the second row. And then the ARs will cancel here. Okay. These are going to cancel, aren't they? Okay. The AR squareds are going to cancel. The AR cubes are going to cancel, and so on, all the way down until I'm just left with AR to the N on the bottom. Now remember, it's the first row subtract the second row. So I'm going to be subtracting AR to the N. Now, please just take that step in for a second, okay, and make sure you're happy with it. So just look at all the cancellation. AR subtract AR, gone. AR squared subtract AR squared, gone. All the way down. But there's nothing to match up AR to the N, and it's because it's in the second row, it's going to be subtracted from the first row. Okay, and just make a note what we've done here. I think it's important. So we subtract second row from the first row. That's all we've done. Okay, now it's starting to look a bit like the formula. Now, if you look on the left-hand side, we can actually factor out the Sn part. Okay, so we've got Sn, and we can write that as 1 subtract R. Okay, and on the right-hand side, I can factor out an A. So I'm going to have A multiplied by 1 subtract R to the power N. And then to get my sum that I wanted, I just divide both sides by 1 subtract R. So the sum of n terms, here it is A multiplied by 1 subtract R to the N over 1 subtract R. Just for completeness, if you did it the other way around, if you did the second row subtract the first row, you can do this as an exercise if you like. The space provided, you'll get the second formula here. Okay, they're both the same. It's just a sign change, okay, in the numerator and in the denominator, so it makes no difference. Right. Okay. Now that concludes that. I think we should just. I think this deserves a bit of highlighting, doesn't it? So this is the sum of n terms. Make it look really important. And remember that the step that you really, really need to remember is to multiply by R and also to subtract, okay, the second row from the first row. All right, so let's have a look at our first worked example. We have a series and we're asked to find the first or the sum of the first 10 terms. Okay, so that's obviously an important piece of information. Just note as well, when we're finding the sum of a series, what piece of information do we need? Well, we need to know the first term. We need to find A, don't we? We also need the common ratio as well. And we also need to know how many terms we're going to sum over. So let's have a look at this series here. Well, first term, that's immediately obvious, isn't it? Okay, so that's just going to be 2. So we'll just put 2 in for our A. Now the common ratio, we can find that pretty easily. If we just do a little bit of side work over here, you notice that if you do 6 divided by 2, well, that's 3, isn't it? And it doesn't matter which terms you select. You could do 54 divided by 18. Okay, you get 3. Okay, it wouldn't be a geometric series if that wasn't true. All right, so that's our common ratio, which is 3. We're multiplying by 3 each time, okay, to get to the next term. And then n, well, n is given to us here, isn't it? We're summing over 10 terms. So it looks like we have everything we need to do our summation. You'll recall that we have 2 different versions of the formula. Now, just let me give you a tip on which one to use. If the R value, which is here, if this R value is greater than 1, in fact, let's write this down as a reminder. Okay, so if, I'll just do it underneath. So if the R value is greater than 1, to avoid having unnecessary negatives, and you might think this is easier, you might not. Just a suggestion, use the, I'll call it the R subtract 1 version of the summation formula. Okay. All right. I hope that makes sense. Just to avoid the negative numbers. Right. Let's use the formula now. So we're going to sub in all the values we know. Right. So we're going to use the R minus 1 version. So that's going to be R to the power n subtract 1 over R subtract 1. Let's substitute in all the values we know. All right, so we have A is 2, R is 3, so that's going to be 3, N is 10, 3 to the power 10, subtract 1. Okay, and then we have R subtract 1 on the bottom. That's 3 subtract 1. And you may want to do a bit of tidying up here. Okay, so that's going to equal 2 multiplied by 3 to the power 10 subtract 1 over 2. And we can do another step here if you like. So this is going to equal just 3 to the power 10 subtract 1, because the 2's will cancel out, won't they? What do we get? Oh, we get 59048. So we can write that in. So this is going to equal, what's a nice color, isn't it? 59048. Okay. And we're done. All right, for works example 2, again, let's just write down what we need. We're going to need the first term, A, we're going to need the common ratio R, and we need to know how many terms we're summing over. All right, it says find the sum of the series. Now, we're given the first term. That's really straightforward. There it is. Okay, we can write that in. So it's just going to be 1024. So that's our A. We can easily find the R just by dividing consecutive terms. So the second divided by the first. Now, just be careful with this. If I take the second term here, it's got a negative sign. Okay, now that's part of the term, isn't it? Okay, we seem to have an alternating series here. So if we do that, we should get negative 512 divided by 1024. Okay, and you'll notice very quickly that will simplify to negative 1/2. All right, you can verify that if you do 256 divided by negative 512, you get the same thing. So this is fine. So we've got our R value. There it is, and we've got our A. So we're almost there. We just need to know how many terms we're going to sum over. Now, this is where we run into a slight problem. It doesn't tell us. It just tells us what the final term is, which is 1. Okay. So at the moment, we don't have enough information. We don't know what the nth, how many terms we're summing over. But because we have the last term or the nth term, perhaps we can find out. So we can see here that the nth term is +1, okay? Or, as we know from previous lessons, un is just equal to 1. Right, now we know the formula for the nth term, don't we? Okay, so this is AR to the power n subtract 1, and in this case, this is equal to 1. Now we have to substitute in what we know. Okay, well, we know A, so I can put that in. So that's going to be 1024. All right. Now R is -1/2. So we have to multiply that by -1/2 raised to the power n subtract 1. And apparently all that is equal to 1. Right. Now you may look at that and think, oh dear, this is a bit complicated. Well, we could use a bit of common sense. I'm going to go through the process of actually finding n from this equation here that I've just written down. We can do it, but if we just use a bit of common sense, what's causing a problem is the fact that we've got these negative signs here, here, and it's alternating. But you can see clearly that each term is half as big as the previous one. All right. So even though we know that R is really, it is really -1/2, don't we? Okay, we can fudge a little bit and just pretend it's not. All right, because we just want to find out how many terms there are. How many times do you have to halve 1024 until you get to 1? Okay, it's essentially what we're trying to find. Now, if you do that, we have a much simpler approach. So I'm just going to do this as a little aside. Okay, I'll do it over in the top corner here. So we'll say, imagine R equals 1/2 instead. All right, and just how many times do you have to halve 1024 until you get to 1? Well, if we do it that way, we get 1024 multiplied by 1/2 to the power n subtract 1, and that's equal to 1. Now, if we just divide both sides by, so I'll just put a therefore in, divide both sides by 1024, we then get this. So we get 1/2 to the power n subtract 1 is simply 1/1024. Now, you'll know from your work on indices that this is just the same as 1 to the power n subtract 1 over 2 to the power n subtract 1. Yeah? So we can just flip it over. And then remember, obviously, 1 to the power anything is just 1. So if we flip both sides over, we're going to get this. So we're going to get 2 to the power n subtract 1 must equal 1024. And you can also see as well, if we just compare numerators and denominators, the 1 to the power n subtract 1 corresponds to 1, and then the 2 to the power n subtract 1 corresponds to 1024. So you can think of it like that. Now, you may know the answer straight away. You may know your powers of 2 really well. If you don't, you can use BAPs from the log work that you did last year. So we have the base, which is 2. We have the power, which is n subtract 1, and we have the answer on the right-hand side. Now, to write it as a logarithm, you simply write it in the order of BAP. So it says BAP. So we take the log, and then the first number to write in is the base, which is 2. Then we write in the answer, which is 1024. Okay, and that's equal to the power, which is n subtract 1. So just so you can see that, we've got the base here, the answer, and the power. So therefore, n subtract 1 is equal to 10. So therefore, n is 11. Right, that you might even think that's quite a lot of work. Possibly, or you could just do it longhand. You could just say, okay, how many times do I need to halve, and then just write out the whole series. You could do it that way as well, and you'll notice you'll get 11 terms. There's really no right or wrong approach to this. It's just down to you and what you're comfortable with. Now, if we just go back to this part here where we have the negative sign, you can deal with the negative sign if you want to. What you can do, let's get rid of that. What you can do is actually sort of factor it out a little bit. So we do the same step. So you're going to have negative 1/2 to the power n subtract 1 is going to equal 1 over 1024. Right. So next you say, well, I can flip them. So this is the same as negative 2 to the power n subtract 1 is equal to 1024. So you've got the same problem, except you have negative 2. Well, how do we deal with this? Well, if you think of negative 2, we could think of this as negative 1 multiplied by 2. And then all of that is being raised to the power n subtract 1. But because we know a bit about indices, we know that we can split two factors and raise them to the power separately. So this would be negative 1 to the power n subtract 1 multiplied by 2 to the power n subtract 1. All right. And that's equal to 1024. And this is where, again, you're going to have to use common sense at some stage here. The answer is very, very, very clearly, it's positive, isn't it? Okay, this is positive. Okay, now 2 to the power n subtract 1, is that a positive or a negative value? Well, if you raise 2 to the power anything, I guarantee you're going to get, you're going to get a positive number. This is always positive. Okay, now we have a product here. What do you multiply a positive by to get a positive? Well, we are forced to make this a positive now. The negative 1 to the power n subtract 1 has to be positive. There's no choice. Okay. So if we think about what that looks like, if you raise negative 1 to any power, it's going to either be positive, positive, or negative. And if it's positive, it's just going to be 1. So we can argue away this and just say, well, this is clearly just going to equal 1. All right, and then we've got the same problem as we had earlier, which we've already solved. We've got just to solve 2 to the power n subtract 1 is equal to 1024, which we've already done. Right, so you may not like that. That's just a different way of looking at it. Maybe a more correct way, but even so, if you don't like either of those methods, you could just simply go back to the series up there and then just write them out if you're really not confident with that. Okay, now the important thing is, from all that working out, we've established what the value of n is. It's here. N is 11. You may have forgotten about that. So let's write it in at the top. So we'll just erase this. We don't need that anymore. So we now know that n is equal to 11. We've just found it. Right, can we find the sum now? I've just put 1. I don't know why I put 1. N is 11. Let's do it. So I'll just partition this off. So the sum of n terms, so S11 is going to equal A, which is 1024. Okay, now notice this time we have R an R value which is not greater than 1, it's probably a good idea to use the 1 minus R version here. Okay, but again, it doesn't really matter as long as you're confident with your negative signs. So we're going to have 1 subtract negative 1/2 to the power 11, close that bracket, all over 1 subtract negative 1/2. Okay, just check that. So 1024 is A and R is negative 1/2 and the power is 11. Right, let's tidy this up a tiny bit. So we're going to have 1024 multiplied by 1 subtract negative 1/2 to the power 11, and that's going to be divided by, well, 3 over 2 essentially. All right, just to finish off. Okay, so a bit long-winded that one, but there was some important ideas in there. Next, we're going to have a look at the sum to infinity of a geometric series. Now, there's 2 cases here to consider. The first case is for divergence, and they'll be the more common series that you'll be familiar with. You'll see a lot of these. So divergence, this is a typical example as well. If you add each of these terms, but continue doing it for infinitely many terms, then as expected, you're going to be adding larger and larger numbers together, and the series is going to just explode towards infinity. Okay, so this is what we call a divergent series. There's also divergent sequences as well. And I just want to show you what we mean by divergence a bit more clearly. So if I just have a look at the nth term rule for this. So we just write down what we know. We know A is 2. R, the common ratio, is obviously 2 because we're multiplying by 2 to get from one term to the next. So that's going to be 2. And if we put those 2 things together, we know that the nth term is going to be 2 multiplied by 2 to the power n subtract 1. And obviously that's using the general form un equals ar to the n minus 1. Now, if we can just bring these 2 powers together, notice as well, we've got 2 to the power 1 here. And if we use laws of indices, we're going to get 2 to the power n for our nth term rule. Now, this is the nth term rule for the sequence. Okay, I'm going to stress that this is for the sequence. Now, what would happen to the sequence as n approaches infinity? Well, it's very simple, isn't it? We can do this on our calculators. So if I just bring the calculator up, we'll just clear what we've got here. All right, I'm just going to erase that as well. So just put in some numbers, big numbers. Okay, so 2 to the power, let's say 100. Okay, we've already got 10 to the power 30. It's just an enormous number, isn't it? So as we approach infinity, and you can keep trying it if you want to, 2 to the power 1000. My calculator can't even cope with it. It's such a big number. Okay, we're going to get infinity. It's absolutely clear, isn't it? So as n approaches infinity, we can see that 2 to the n also approaches infinity, but much more quickly. Right, so that's an interesting result. Now let's consider the series. Okay, now we've got A, we've got R. What about the sum of n terms? Well, if we do the sum of n terms, this is going to be A multiplied by, now we're going to use the R subtract 1 version. So that's going to be 2 to the n subtract 1. And then we're going to divide that by R subtract 1. So that's going to be 2 subtract 1. And we can simplify that to 2 multiplied by 2 to the n subtract 1. So this here is an expression for the sum of n terms of our series. Okay, so this part here, this tells us what's happening to the sequence. So each term is getting bigger and bigger and bigger and approaching infinity. But obviously, as we're adding terms, so we're going to also approach infinity. And we can see that clearly, can't we? Because if I just click on here, notice that we have the 2 to the power n appearing again. Okay, we know that that approaches infinity, don't we, as n approaches infinity. So clearly, this is going to approach infinity as well as n approaches infinity. So this is what divergence is. It's when your sequence or your series, both in fact, approach infinity as your n value approaches infinity. Now we're going to move over to the idea of what convergent is. So convergence. So convergent sequences don't behave like this, and you'll see why. Now, if we consider the sequence again, first of all, we've got A is going to be 1, and my common ratio R is a half. And let's write down the nth term rule. So un is going to be A multiplied by R to the power n subtract 1. So in other words, it's just a half to the power n subtract 1. And we dealt with this in questions 3 and 4 of the warm-up, didn't we? We actually considered this limit. We drew the graph, and I think we saw explicitly what's going to happen. So we know as n approaches infinity, just remember what happens to a half to the power n subtract 1. Well, we know that that is going to approach 0. Okay, that's a very important result. So it's not diverging, okay? This is what convergence is. If each of those terms of the sequence, this is not the series now, if each of the terms of the sequence gets smaller and smaller and smaller, so that as n approaches infinity, the terms become closer and closer to 0, this means that the sequence is convergent. Now, let's see what the behavior is like of the sum of the series now. So if we look at the sum of the series, Sn, we're going to use the 1 subtract R version this time. So it's going to be A, which is 1, multiplied by 1 subtract 1/2 to the power n, close the bracket, over 1 minus R. So that's going to be 1 subtract 1/2. Now we can just tidy this up a little bit. We're going to have 1 subtract 1/2 to the power n all over what is effectively just going to be a half. Now, in other words, if I multiply, put top and bottom by 2, I'm going to get 2 multiplied by 1 subtract 1/2 to the power n. I think that's the best way to write it. So this is the sum of the n terms. Now notice we've got our results appearing again. Now it doesn't say n minus 1, but obviously when you're getting close to infinity, adding or subtracting 1 to your number is not going to make much difference. So we can say with confidence that this term here, the half to the power n, is going to approach 0. This is going to go to 0 as n approaches infinity. Okay? Now, what's the repercussions of this? Well, we can say now that as n approaches infinity, our sum of n terms is going to approach, well, what is effectively going to be 2 multiplied by 1 subtract 0. Okay? Which is, in other words, is 2. So it's not going to explode to infinity. It's going to converge on a particular value. Okay? In this case, 2. Now, this is quite a staggering result. So what we've just shown is that if we take this series here. So you start with one whole, you add a half, then you add a quarter, then you add an eighth and a 16th, and then a 32th. If you keep doing that, your answer is going to get closer and closer to 2. And I do suggest you try this. You can do it on a spreadsheet. Just add more and more terms, and then you'll see that the answer gets close to 2, but never, ever quite gets there. So now let's have a look at the derivation of the sum to infinity. Okay. Now, the first way we can use limits. All right. Now, we saw previously that when you have a convergent series, the sum will converge on a particular value. Also, the sequence itself, the terms in the sequence will converge to 0. Right, let's have a look. So let's just do it generally. So we know for any for any geometric series, this is the sum of n terms, isn't it? Okay. Now we've seen from the example just above that as you let n approach infinity, r to the n seems to approach 0, doesn't it? Now, just think about why that is. It was something to do with the value of r, wasn't it? Okay, and we'll see why more in method B when we use the binomial expansion. But that's the behavior. When you raise your r to the power n, it seems to approach 0. So if we apply this, so the limit as n approaches infinity of our sum is equal to the limit as n approaches infinity of a multiplied by 1 subtract r to the n over 1 subtract r. Okay, now this is how we write it. I've put the limits on both sides for a particular reason. Okay, it's just for the notation. So notice that the n is approaching infinity here. So when we write the next step, we can replace this n here with infinity. And that's the notation for the sum to infinity. So therefore, the sum to infinity is going to be equal to, okay, and let's deal with the right-hand side now. Well, we know from what we've just said, from this step here, that is just going to approach 0. Okay, this is going to 0. So we're left with this. Okay, so we're going to have, in other words, a multiplied by 1 subtract 0 over 1 subtract r. So this is going to be the sum to infinity. So you're just going to be left with a over 1 subtract r. All right. And you can just test this. Remember in the example previously, we saw that a was equal to 1 and r was equal to 1/2. Well, if we sub those into here, you'll see that you get the answer 2, which is what the sum to infinity was. Okay, that's the value it tends towards. All right. Okay, so that's a really important formula. Let's make that look really important. Let's make it look all colorful. So that's the sum to infinity. It's a really nice formula, and you'll be pleased to know this is given to you in your formula booklet. Okay, along with the sum of n terms of a geometric series as well. Okay, so it's nice and simple. Now, let's just explore the second method using the binomial expansion. Now, this won't take long because we've done this already in warm-up question 1. So I'll just put C warm-up question 1. You've already done this. It was nice revision, wasn't it, for the binomial expansion? And you saw that a over 1 subtract r is indeed the same as a plus ar plus ar squared plus ar cubed forever and ever. Okay, and this is where we can see this slight caveat. All right, this is only valid, isn't it? It's only valid if we are careful about the values of r that we use. Okay, these values of r have to be constrained. Okay, otherwise this won't work. You can't just do a binomial expansion for anything and sub in whatever you want to. And you'll know from the expansion that we did earlier that the R value has to be between -1 and 1. And this makes sense, doesn't it? Because when you raise fractions, so proper fractions, to powers or multiply by other proper fractions, the values get smaller and smaller. Okay? So that's the reason. So we also have to bear in mind that we have this restriction here. All right? So that is also very important. And you can't have one without the other. So they go together. So I'm going to stress it again. You can only use this if your R value is between -1 and 1. Okay? And then you can apply that formula. Now, for the first worked example, we've already touched on this, so I'm not going to go into a great amount of detail. And we've also got this really nice visual representation of what I was talking about before. All right. Okay, so let's just have a look at what the sum to infinity of that series is. Okay, for the sum to infinity, we can just state the formula for that. And just put the restriction of R on as well, because we have to apply that. Okay, and let's have a look what we've got here. Well, we've got basically what we saw earlier. A equals 1 and R equals 1/2. And we know that that is absolutely fine because it lies within this interval. Okay, so we can use, just make a note, so we can use S infinity. Okay, so it has to be follow that restriction. So let's do it. So sum to infinity is just going to be A, which is 1 over 1 subtract 1/2, which is 1 divided by 1/2, which is equal to 2. Okay, and there you've got it. So that's your sum to infinity there. Okay, let's have a look at some problem solving type questions that you might get in an exam. Okay, so this one you're told the sum of the first 4 terms of the series is 15, geometric series, and the sum to infinity is 16. Well, we have everything we need. We've got the formulas, they're provided for you. So let's write down what we know. So the sum of the first 4 terms, S4 is equal to 15. And the sum to infinity, that's so S infinity, is equal to 16. Right. Well, what does that tell us? Well, we have formulae for these, don't we? We have in the case on the left-hand side, S4, we know that N is equal to 4, don't we? Okay, we don't know what A or R are, but we can now write down the formula. So this means that if we do A, and I'm going to write it in a particular way. I'm going to show you why in a second. So 1 subtract R to the power 4 over 1 subtract R. We know this is equal to 15. Okay. I'm using the 1 minus R version because we know this has a sum to infinity. All right. So just make a note here. So we know that R must be between -1 and 1 because of the fact that the sum to infinity up here exists. Okay, and remember when R is between -1 and 1, we use this version of the formula. Okay, it's just so you're clear about that. It doesn't matter if you don't, but I just want to make you aware of it. And then we also have the sum to infinity, don't we? So let's just write out the sum to infinity. So we also know that A over 1 subtract R is equal to 16. Okay, that's good. Well, how does this help us? Well, we could, in theory, I mean, we've got 2 equations here, haven't we? We could call this one equation 1, with two unknowns in it, a and r, and equation 2 here with two unknowns, a and r. Rearrange and solve them simultaneously. We could do that, but if you notice, there's something quite nice going on here, and I can show you very clearly using a highlighter. If you, I'll try to, there we go. If you look that we've got a over 1 subtract r here, it also appears in equation 1, doesn't it? So I can replace all of that a over 1 subtract r on the left with just 16. Let's do that. So just show you where. So that features over here. So therefore we have 16 multiplying 1 subtract r to the power 4 is equal to 15. And I'll highlight it in green again. So this is what I've replaced. Okay, with one, I've replaced a over 1 subtract r with 16. So this is just equation 1 rewritten. Notice that this has eliminated a. So I can now divide by 16, or you can expand it. It's up to you. So therefore, 1 subtract r to the power 4 is equal to 15 over 16. Let's just rearrange this again. So I'm going to add r to the power 4 to both sides and subtract 15 over 16 from both sides. Okay, and then let's just jump up to this side of the screen. So this is 16 over 16 minus 15 sixteenths. So we have 1 over 16 is equal to r to the power 4. And just be careful here, because I've seen students and they'll see this and they'll go, oh yeah, r is a quarter. Well, there's two things wrong with that. It's the fourth root, isn't it? So the fourth root can obviously take positive and negative values. And the fourth root of 16 is not 4, that's the square root. It is, of course, a half. So therefore, r is going to equal plus or minus a half. All right, and that's that one done. So that was part A, wasn't it? I should just indicate that up here. This was part A. And for part B, it says, given that all the terms in the series are positive, so I'll just partition this off, find the first term A. Okay, so for part B, so given all terms are positive. Now, what that means is that implies that your r value, if that's the case, has to be greater than 0. Okay? And if that's true, that must mean that the r value we must take must be a half. Okay, so we're going to have to use r equals a half for this. There it is. That's what we're going to use. And we have to find the first term a. Okay, so we can just sub this into one of our equations. So obviously I'm going to choose equation 2 because that was the easiest one. So we'll say that. So we're going to sub r equals a half in equation 2. If we do that, this is what we're going to get. So a over 1 subtract a half is going to equal 16. So therefore, a over a half equals 16. And just to finish off, that implies that a is, well, multiply both sides by half, so a must be 8. Right. And you can check all of this on a calculator just to verify that it's true. Now, example 3, this is our final example. And this is very much like what you might see in an exam relating to this topic. So we have this equation given to us, and it looks a little bit unusual. Okay, we're told that the sum of the first 4 terms of a geometric series is equal to 8/9 of the sum to infinity, which does make sense, doesn't it? Because the sum to infinity would just be slightly higher Yeah, if you're adding smaller and smaller pieces each time, smaller and smaller terms. We have to show that R is in this form. Well, let's just make a note of what we can deduce from the formulas that we already know that are given to us in the formula book. So we know that S4 is equal to A multiplied by 1 subtract R to the 4 over 1 subtract R. We know that. And we know that the sum to infinity is just A over 1 subtract R. And we're not given either of them. We're just given an equation with both of them in. So how could we do this? Well, there's lots of different ways you could do this, really. Let's set the equation up. So it's 8/9. So S4, which is A multiplied by 1 subtract R to the 4 over 1 subtract R, is just equal to 8/9 multiplied by A over 1 subtract R. And I could have even written this all in terms of sum to infinity. Okay, maybe we could explore that later. Now, there's different ways of doing this. It is a case of just tidying everything up. Now, what I'd like to do is I'd just like to try to factorize this, because you can see probably straight away that we have A as a factor on both sides. Okay, so A is going to cancel. All right, so you don't need to worry about A. So this is just going to be purely an equation in terms of R. So that's going to cancel and just to leave us with 1. Okay, like there. And then we have 1 subtract R on both sides. Now we can multiply both sides by 1 subtract R. Okay, so if I do that, that will clear it because it's in the denominator on both sides. Now, when we do that step, we're going to get this. So we're just going to be left with 1 subtract R to the power 4 is equal to 8/9. Very quickly. And we have the same situation as in the previous example. If I add R to the power 4 and subtract 8/9 from both sides, like so. Okay, this is going to leave me with R to the power 4 is equal to 1/9. Now you'll notice that this is not a particularly nice answer, and we were told earlier to write it in this form. Okay, now what you can do if you want to do it this way, we could actually write it as a difference of 2 squares, because I just want to show you what's going on here. So what I mean is, if you write R to the power 4 subtract 1/9 is equal to 0, and just note that this is R squared all squared subtract 1/3 all squared, like this, and this equals 0. And then we can put that into brackets. So in other words, you're going to have R squared plus 1/3 multiplied by R squared subtract 1/3, which equals 0. So either R squared is equal to negative 1/3, or R squared is equal to 1/3. Now you'll notice if we're going to find the square root of R squared, in other words R, we cannot deal with the one on the left hand side, because you cannot take the square root of a negative number and get a real value. But we can square root this. So R is going to be plus or minus 1/√3. And I believe that's the form that they want. So in other words, K equals 3. Now, just as one possible alternative approach to this, just another way of thinking about it. When we start off with the two equations at the top here, these two, remember these are in the formula book. You just look these up. There's nothing wrong with that. You could actually write an equation just in terms of the sum to infinity. Because we know that the sum to infinity is just a over 1 subtract r, we can use the same idea that it appears in the sum of n terms formula as well. So what I could actually have done, and this is just personal preference, but I just want you to be aware of it. We know that S4, which this is given to us in the question, is equal to 8 over 9 multiplied by the sum to infinity. Well, we can write S4 like this. It's the same as the sum to infinity, isn't it? Multiplied by 1 subtract r to the power 4. Yeah? So if I write that in, I have s to infinity multiplied by 1 subtract r to the power 4 is equal to 8 over 9 multiplied by the sum to infinity. And this way you can cancel the sum to infinity out on both sides. Okay, and then you're left with the same step as you got over here. So it's just personal preference, that. Okay, and I just want you to be aware of it. And I think that concludes the lesson. So thank you very much.